Greetings, this is John, or Lynn as most of you probably know me as that's my online alias. Today we're going to be starting a project that I've been wanting to do for a really long time now. It's gonna be a Let's Play style programming project. I'm going to go ahead and just start this right now. Some of you might know this, most of you probably don't, but I've been researching isosurface extraction for quite a while now, just been experimenting with a bunch of various algorithms. The latest video I have on my channel as of right now is on manifold dual contouring, but I've definitely been doing other stuff since then. And what I have here is just the experimental code from one algorithm, which I call diamond marching cubes. I don't really think it has a name, but basically it uses a tetrahedral hierarchy and then runs marching cubes on the tetrahedra. Basically, that's how it works. And so this is all done in C# using X and A. Here's what the wireframe looks like. So as you can see, it's definitely got some level of detail support, and we can change the model. It might take a moment while it loads. Here we have another dragon. And this is cool and all. It's kind of optimized, but at the same time it's also not. Right now it's not dynamic, it just supports a single extraction phase. I have not implemented dynamic level of detail as the camera moves. I've started some of it, but not gone all the way. And the project that we're going to be starting is actually porting this over to C and using OpenGL. And the reason for that is so we can get the most out of our hardware, I guess would be the term for it. Basically, we're looking to optimize it and get it to be super quick. Now you guys might be able to see it, might be able to not. I don't even know if this is recording in 1080p. Gosh, I sure hope it is. But this whole scene, about 44,000 triangles, took about 730 milliseconds to extract, which is not bad at all, but we definitely want it to be faster, and so that's what we're going to be trying to accomplish. Now, one other thing that I've been working on as well is an idea that basically builds off of dual marching cubes, where it extracts the dual grid and then runs marching cubes by dividing those nodes even further. And then I'll go ahead and switch over. Now, I'll just zoom out real quick. Look at how this mesh looks. Again, about 44,000 triangles. I'm going to put the camera right around here, and then I'm going to hit tab, and tab is going to switch the algorithm into that one. The one that it's switching to now is actually the first one that I had implemented, and the idea that I got the idea just based on reading the paper for the tetrahedral stuff, and didn't quite wrap my head around it, and this one came to me, so I implemented it. And honestly, it's amazing. I really think that this is a good idea and it has a lot of potential. Has a couple problems, namely it took almost 6 seconds to extract this mesh, and it has about 75,000 triangles, so it's a little bit slower, but at the same time I have not multi-threaded it like I did with the other algorithm, and I have not given it as much attention or attention or focus as the other algorithm. Basically, we're going to be deciding which algorithm is going to be better to implement, and then kind of go from there. Okay, now one thing that I'd like to address with the dual marching cubes based algorithm is the transition cells, unfortunately, when they are a special corner case, produce artifacts like these with really slim triangles. Not really noticeable on the outside, but then when we start getting closer in here, here it's very noticeable. You can see these really tiny triangles, and then they usually come to a box like that. You can especially see them here. Oh yeah, one thing that I forgot to mention is that the size of that mesh was 2 to the power of 18, so that comes out to about 262,000. So that's the size that we were dealing with there. So one other thing that I wanted to bring up regarding the quality is I have considered and would like to use post-processing. Here's a basic terrain scene. I say basic, it's not really basic, but just some quick noise generation with location smoothing applied to the resulting mesh. And so here's what we get, and honestly it works very well. As you can see, there are a lot of equilateral triangles, and then even when we get in here, this is like my favorite thing to test, by the way, because it's just so cool to have all this detail. And this one here is 2 to the power 16, obviously about 65,000 is the resolution that we're dealing with. So we can zoom out. And we have about 96,000 triangles, and this took pretty much exactly 3 seconds to extract, including all the noise generation. And then we can switch over to the dual marching cubes based algorithm. This is probably going to take a while, like I said, not really optimized, and considering this took 3 seconds, it'll probably take this one a while. Wow, I must say I was not really expecting this as the result here. It took about 37 seconds and we have about 200,000 triangles. I mean, certainly looks nice for the ones that we can see. This is really weird. But anyway, what happened here was the Laplacian smoothing. I did something to it before testing, and then this was the result. Pretty cool, but I mean, it overall kind of looks better. Oh man, C++ compiles so slowly. Okay. So this is something else that I wanted to show real quick. For a little while I was experimenting with advancing front. If you don't know what that is, it's basically an algorithm where it starts with one C triangle and then it just builds upon each edge of the triangle and then creates another one, and then so on and so forth until you have a fully complete mesh. And so this here, it's actually not from the same project, it's from another one. I call it Project IW, and I actually have this on GitHub. I don't know if this latest stuff is published or not, but as you can see, the resulting mesh is just astoundingly high quality. Almost everything is an equilateral triangle, and if not, it's very close. Obviously, a mesh can't all be equilateral, but the idea behind this was to create a chunked-based system and then implement level of detail with it, and it looks pretty cool. I really like the way that it looks, but just unfortunately it's too slow. Here's what it looks like without the wireframe, by the way, just in case you were curious. Very, very nice stuff. Alright, so that brings us to the conclusion of this first introductory episode, which is, how far have I gotten with the C project with OpenGL? Well, here's all the code I have, and if you have Googled for OpenGL tutorials, you probably will recognize most of this. I'll run it real quick. This is what we have. We have a triangle. No specified projection or camera or anything like that, just a simple triangle, but you have to start somewhere. I honestly haven't used OpenGL from scratch. I've used SFML, and that's pretty much all my exposure to OpenGL. So it's a little bit of a learning experience, and I hope to share that with you guys along the way. Hopefully we'll be able to make some pretty cool things with this. I'm honestly excited. In episode 2 we'll probably go into, I don't know if I'll show it or not, the camera creation and then actually getting somewhere to where it's a 3D world, and then we can actually start porting some code over. So hope to see you then. Thank you all for watching, and I'll see you next time. Oh guys, one last thing before the video ends, be sure to check out voxelspace.net. It's a forum that I've started recently. Not a whole lot on there as of the time of this recording, but it's supposed to be a community where people can go to get help and ask questions and find tutorials and stuff, and a place for me to kind of post what I found. Again, in time it'll all come out, but be sure to check it out and hopefully register and stick around.